Hi, I'm Matt York, and I am going over our homework for Transport 2 in Dr. Ko's class. This is our second homework of the year, and here we are going over in the first question, we're going over a capillary tube system which is closed, similar to the one we did in the first homework. And this has water on the left side and deteriorated water on the right side. And what we're trying to find here is the mass flux of this entire system. Well, how do you find the mass flux of the entire system? Mass flux is equal to the mass flux of each of the components in the system summed together. So we have mass flux of water and the mass flux of deteriorated water, and we're going to try to find both of those and sum them together, and it should give us the total mass flux. So going into this equation, things we know based on a closed capillary tube system is that when this divider is removed, these two components are going to start diffusing into one another because there is no empty space in this capillary tube. So say when water starts diffusing into deteriorated water, deteriorated water is actually going to diffuse right back into water at the same rate because water's not going to leave this empty space. It's going to be filled with deteriorated water. Well, knowing that and knowing that we have the maximum diffusive flux of knowing that we have the maximum molar diffusive flux, sorry, excuse me for my wording there, maximum molar diffusive flux in this system is 2.78 moles, moles per meter squared seconds. We know that the opposite, that whatever component we define as the maximum molar diffusive flux, the other component is going to be the exact same rate, but the opposite direction. So, as water is moving 2.78 or diffusing at 2.78 moles per meter squared seconds to the right, we know deteriorated water is actually diffusing 2.78 moles per meter squared seconds to the left, so it's negative. They're equal but opposite. Well, another thing we know, based on a closed capillary system, as we defined last time in our homework, is that the molar flux of a system is zero when it's a closed system because these two, as we just said, are diffusing into one another at the same rate. So the molar flux to the right and the molar flux to the left are going to be equal but opposite, and the total molar flux will always be zero. And knowing this and knowing the definition from the book, that the mole fraction of a component times the molar flux of an entire system is equal to the concentration of a component multiplied by the molar velocity of an entire system. We know that if the molar flux is zero, this side's going to be zero, and we know this side needs to equal zero. Well, there's a positive concentration here. We have concentration of deteriorated water and of water, so we know that the molar velocity of this system has to also be zero. Well, knowing that and seeing another definition from our book, the definition of the component of a molar flux, the molar flux of a certain component, sorry, excuse my wording again there, but the molar flux of a certain component is equal to the molar diffusive flux of that component added to the concentration of that component multiplied by the, there you go, molar velocity of the system. Well, the molar velocity of the system is zero, so we know that the molar diffusive flux of a component is equal to the molar flux of a component in this system. Well, going to that, we know that the molar diffusive flux of water is 2.78, so the molar flux of water is also 2.78. Well, the great thing is, as we defined, we know that the mass flux times the molecular weight is not the molar flux. We determined that in our last homework. But what we did find out is the molar flux times the molecular weight is the mass flux. So knowing the molar flux and knowing the molecular weight of each of these components, deteriorated water is given in our problem, and water we just know is 18.02 grams per mole off the top of our head. So we have the mass flux of water is 18.02, as I just defined, the molecular weight of water multiplied by the molar flux 2.78 of water. And then we have the mass flux of deteriorated water is equal to the molecular weight of saturated water, which is 20, multiplied by the molar flux of saturated water, which is negative 2.78, because it's going in the opposite direction. Both of these, the mass flux of water turned out to be 50.1, and the mass flux of saturated water turned out to be 55.6. Negative 55.6 due to this negative sign, and when we sum these together, we get negative 5.5 grams per meter second squared is the mass flux of this entire system. So going on to question 2 here, we are trying to find the what's it called? The driving force. Trying to find the driving force, an estimate for the driving force of this system. So when it's at 0.1 seconds. Sorry, forgot about that part too. Well, knowing an equation that's defined in our book, where the driving force for a system with two components is equal to the molar diffusive flux of one component times the mole fraction of the other component, subtracted by the molar diffusive flux of the other molar diffusive flux of that second component, multiplied by the mole fraction of that first component, divided by the concentration of the whole system, multiplied by the Stefan Maxwell law, or constant of diffusivity. I can't say that, sorry. The Stefan Maxwell constant of diffusivity, which for liquids, as we are here, in terms of meters, it is 10 to the negative 9th. So we'll put that in later. But the things we do know, we already have the molar diffusive flux of saturated water and of water, but we do not have the mole fraction of each of these components, and the concentration we don't necessarily have either. So we're going to worry about those right now. Well, one thing we do know is that the mole fraction is each component added up equals 1. So there's two components, and we have saturated water, so mole fraction of saturated water and mole fraction of water summed together is 1. We do know that. So we can try to substitute one of these, manipulate this equation and substitute variables in so that we have one variable, and then hopefully we can cancel each other out. So let's go for that. So we have negative 2.78, which is the molar diffusive flux of saturated water, multiplied by the mole fraction of water, subtracted by the molar diffusive flux of water, 2.78, and then we're going to substitute in 1 minus the molar fraction of water for the mole fraction of saturated water, because we defined that over here in this equation. Well, when we do that, we figure out that we have negative 2.78 mole fraction of water and 2.78 mole fraction of water. So these actually cancel out. We don't even have to worry about finding the mole fraction. So that leaves us with negative 2.78 divided by the concentration of the system over the Stefan Maxwell diffusivity constant. Well, we already know both of these numbers, so we need to find the concentration of the system. Well, how can we find the concentration of the system? What is concentration, you may first ask? Concentration is moles over volume. Well, we do have density, and we do have molecular weight, which gives us concentration, because the density divided by the molecular weight, which is mass over volume density, divided by mass over moles, which is molecular weight, that gives us moles over volume, which is concentration. So we're going to take the, okay, so that's how we can find concentration. But what is concentration of a system? Is it just the sum of the concentrations, or how do you find that? Well, what it is it's the sum of each component divided by the number of components. So sorry, that's an X right there, because we don't know, there's 2 in this situation, but we don't know how many there's going to be. Well, there's 2, so we have the concentration of water and the concentration of saturated water summed together divided by the number of components in the system. That's the concentration of the system. Well, we can find these very easily. We just take the density of water, which we know is 1,000 kilograms per meters cubed, and then we divide that by the molecular weight of water, which is 18.02 grams per mole. That gives us 55.5 times 10 to the third. And for saturated water, we know, based on what's given in the problem, that the density is 1,110 kilograms per meters cubed, and the molecular weight is 20 grams per mole. So dividing the density by the molecular weight here, we get 55.5 times 10 to the 3 for also, or 10 to the third, also for saturated water. Well, we have two components here, so we divide by 2, and we get the concentration of the system to be 55.5 times 10 to the third moles per meters cubed. Well, going on from that, we plug that into our driving force equation, and we plug in the Stefan-Maxwell constant diffusivity, which we defined earlier as 10 to the negative 9th for liquids when we're in respects to meters, which we are in this equation, and we get negative 5 times 10 to the 4th 1 over meters, which is driving force. So our estimate for driving force, since it's 10 to the 4th, we know is our estimate would be 10 to the 4th when going into terms of magnitude. So going on to our third and final question of the day, we were asked to sketch graphs for different mass transfers in this system. Well, we're starting off with the mass concentration transfer, and this is in regards to position in centimeters, which we defined earlier. Let's pull this up. 0 centimeters is on the left, 10 centimeters is on the right, 0 centimeters to 5 centimeters is the water, and 5 centimeters to 10 centimeters is the saturated water. Well, we know that right at the beginning, there's not going to be any saturated water from 0 to about 4 at least centimeters, because it's all just water. Well, then as water goes down, at about around this middle point, right when we open this up, it's going to be diffusing. So it's going to be a mixture of both of these, water and saturated water. Well, then at the end, there's going to be no water on this side because it's all saturated water. Well, saturated water is exactly the opposite. Oh, well, sorry, I did say there's going to be no saturated water over here. I meant there's also going to be complete water because it's all water over here. Well, going over to saturated water, we have no saturated water in the first 4, at least, because this is where it's just going to be all water at this point. And then it's going to have some diffusing, and it's going to go up and up as we go further to the right, where we know it's all saturated water. But this is going to be diffusing between water and saturated water. That's why there's a mixture there. And then at the end, we're going to have more saturated water, actually all saturated water, because we're still over here on this right side where a lot of it hasn't diffused. One thing to also note here is the saturated water line is higher than the water line, where from about 6 to 10, where there's all saturated water in comparison to 0 to 4, where it's all water, because saturated water has a higher density, which, as we know, mass concentration is mass per volume, mass of a component per volume, not mass of the whole thing, that would be density, but mass of a component times volume, or divided by volume, my bad. So going into the intermediate, as these start diffusing more and more and more, it's really just going to, you're going to have way more on the right side, because not all of this is going to be diffused yet, but most of this is going to be diffused. So on the left side, there's going to be the least amount of saturated water, and on the right side, there's going to be the least amount of water. So they're just going to gradually change as this diffuses out. And then at the end, when this whole thing has diffused, we're going to have just a constant mass concentration of saturated water and of water, and saturated water is going to have a higher mass concentration due to it having a higher density. Going on to the next question, we have concentration. So we're talking about concentration instead of mass concentration this time. And since these have exactly 50-50 concentration, half of it's water, half of it's saturated water, we know that they should start the same, or they should be the same height in regards to where all of their component is. So from, again, we go back to here, we go to 0 to 4, it's going to be all water. and then about 6 to 10 is going to be all deteriorated water. In the middle, we're going to have this diffusing, just like up here. It is still diffusing, but the difference is we're not going to have a higher higher concentration like we do with mass concentration of deteriorated water, because it's actually 50-50. And then just like the graph above, as these just go and diffuse more, we're going to have it growing for deteriorated water as it goes to the right side and decreasing when it goes to the left side for water, because, or sorry, decreasing, yeah, okay. It's going to decrease for deteriorated water when going to the left side, and it's going to decrease for H2O when going to the right side of this tube, because that's where they started from, giving us this graph. And for final determination of the concentrations, there's just going to be a 50-50 mix of both of these throughout this whole tube. So it's just going to be one just flat line where deteriorated water and water are actually equal, because they both are 50-50 concentration. So going on to the molar diffusive flux, if we're determining this mass transfer in molar diffusive flux, we know that initially the what am I trying to say? We know that initially the molar diffusive flux is 2.78 is the greatest. That's the maximum. And we know that negative 2.78 would be the maximum diffusive flux for deteriorated water, because it's going the exact opposite direction. So we have water is going to not be diffusing at all from 0 to 4, because it's still water, and deuterium is not going to be diffusing at all from 6 to 10, because it's still water. Now right here in the middle we will have a lot of diffusion, and we know that it gets all the way up to 2.78 for water, and it gets all the way down to 2.78 for deuterium, which is essentially the same, but that's the one we picked on going left. So it will look like this. Now going on to the intermediate phase, we know that more of the deuterium is going to diffuse in the middle over here. There's going to be more deuterium diffused, and there's going to be more water diffused over here, and there'll be less on their respective outsides. So it will go increase as it gets to the middle, and then decrease as it goes to the other outside, because there's not going to be much water right here diffusing or right here diffusing. Same goes with deteriorated water. There's not going to be much deteriorated water here and here diffusing during the intermediate, so it's just going to increase and then decrease, but the exact opposite way. Well, at the end, these will completely be diffused, so it'll just be half water, half deuterium, or deteriorated water, just dispersed out throughout the tube, so there'll be no diffusion occurring, and they'll both not be diffusing anymore. Going into the last part of this problem, the mass flux. If we are looking at the mass transfer in terms of mass flux, there is no mass transfer at the beginning, because again, all water on this side, all deuterium on this side, and this actually should just be in one color. I just highlighted it that both of them are doing the same thing, because this is mass flux for the whole system. It's not for each component, because yeah, that's how it is. It's the mass flux of the whole system. So pretty much there's no diffusion on the outsides, no water diffusing over here, no deteriorated water diffusing over here. In the middle where it diffuses, the mass flux goes to what we figured out it was initially, as we found out in problem 1, which is negative 5.5 kilograms per meter second squared. And then if we do it intermediately, it's actually just going to, the mass flux is going to get to this negative 5.5, but it's going to go a little bit more, it goes really sharp here, it's drastic, but when it's intermediate, it's going to be transferring through, since it's going to be diffusing, it's going to be transferring mass flux as well, and it will happen just more dispersed out, if you will. and then at the end there will be no mass flux because there's no diffusion occurring. So pretty much just Jurassic mass flux, very just I can't think of the word right now, I'm sorry, but drawn out mass flux. It's just going to keep getting more mass flux as there's more diffusion, and then as there's no diffusion left, there's no mass flux left too. Thank you so much, and I hope you I hope this helped. I hope you enjoyed this video, and I hope you have a great day.